And here we are again at the Yellow Submarine project. So it's taken a bit of a turn, but I'm happy. Basically, just to catch up with the previous videos, I kind of open up the box of CV quantum computing, which I didn't expect, and so I'm trying to learn a little bit more about that before I dive into the code here, and I even try to run that myself to sort of break down a bit the project. So here in the GitHub repo, you have like the actual solver class, and then exactly. So we went through that in the first video, and I was basically so Josh basically replied to one of my tweets saying that there is a part of the documentation where you can see some neat GIFs. Let's see how that looks like. So okay, CV quantum gate visualizations, gallery and links. Where's that? It's a bit hidden. Okay. Boom, 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 boom. So basically, okay. So you see kind of what the gates are doing. That's crazy. Okay. So in a conventional quantum circuit, qubits represented by wires are operated on by a quantum gate by quantum gates, which collectively perform computations. Similarly, continuous variable quantum computing uses Q modes that represent bundles of interacting photons. Okay, bundles of interacting photons. To perform computations on Q modes, we leverage Gaussian and no-Gaussian gates. Gaussian and no-Gaussian gates can be described within the phase space. This space is shown by the position and the momentum axis. Okay, so this is what I was reading in the appendix of the paper. I think it's this paper here. No, that's something else, I think. No, that could be it. Because yeah, exactly. So I was taking a look at this, and that was basically that's a pretty good summary. Okay, so so now so it's about the phase space, whatever that means. But maybe I mean, at the end of the day, it's quantum mechanics, right? So I think talking about the phase is still something that it's pretty sort of at the technical level, at the physical level, but it still makes sense. And then this space is shown by the position and momentum axis. So I'm guessing that's what we're going to see in those visualizations, position and momentum somehow. Gaussian gates such as the squeezing and rotation gates act linearly on modes. Okay, squeezing and rotation. These gates can only reach positive quasi-probability distributions and can be classically simulated. Okay. On the other hand, non-Gaussian gates such as the Kerr gate and cubic phase gate act non-linearly. This property allows them to be in a negative quasi-probability distributions. In negative quasi-probability distributions, whatever that means, and not be classically simulated. Okay, it cannot be. In this notebook, we'll learn about various single-mode Gaussian and no-Gaussian gates and apply them to a state using strawberry fields. Vacuum state. The vacuum state is the lowest energy Gaussian state. It has no displacement or squeezing in the phase space. Here we learn how to create a vacuum state on a quantum circuit with one Q mode. Okay, so this is more like initializing stuff. I mean, I'm going to skip that for the moment. It's interesting. So you sort of like an engine, like a Gaussian engine. Okay, should be noted that the default state in strawberry fields is the vacuum state. The above gate is listed to show the operation. The strawberry fields, there are three main backends that can be used for. Okay, no, but maybe it's interesting. So three main backends. The backend selected will depend on the task you want to perform. We've used the Gaussian backend to run our vacuum state circuit. We can also alternatively use the Fock backend to run the circuit. The third backend is the TensorFlow backend, TF. It leverages TensorFlow to create quantum machine learning models. Using matplotlib, we then plot the Winga function to the vacuum state, which is a Gaussian distribution. The Wigner function quasi-probability illustrates negative and positive regions in phase space. We'll notice below the Gaussian states such as the vacuum and squeezed state are in the positive regions of the phase space, while non-Gaussian states can reach negative regions of the phase space. The y-axis on this plot can describe the p quadrature or momentum operator, and the x-axis describes the x quadrature of position or position operator. Okay, so y-axis is momentum and x-axis is quadrature. Now it's the z-axis. We can make a couple of observations from the Gaussian distribution above. So this is the Wigner, whatever that is, function, which basically takes your state into a Gaussian distribution. So what I'm having that feeling that this is pretty much going to be about creating kind of probability a la probability distributions, sort of like similar to, I mean, it's not what the D wave people do, because that's more like the energy function thing. And but I wonder, I can do a quick search. I wonder whether there's anything here regarding entanglement and superpositions and stuff like that, or is it really just all about exploiting this stuff? The y-axis on this plot can describe the p quadrature momentum operator, and the x-axis the x quadrature. Okay, so so here we've got the Wigner, whatever, and then so this is basically like a Gaussian. So we can make a couple of things from the Gaussian. We notice that it's positive quasi-probability everywhere. Later, what is quasi-probability? What is quasi-probability? A quasi-probability distribution is a mathematical object similar to a probability distribution, but which relaxes some of Kolmogorov blah 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 axioms of probability theorem. Okay, I don't think I need to dive into this. Certain general feature is crucially the ability to yield expectation values. Okay, yeah, whatever. So it's not like it's not in theory like a pure like probability distribution. Okay. Later on, we'll have a look at the non-Gaussian gates that have regions of negative quasi-probability. The vacuum state is also centered at 0 in both the position axis and the momentum axis. On both the position axis and okay. So squeezing gate. The squeezing gate can also be thought of as a transformation on the position and momentum axis. The squeezing gate scales x to this and scales p to this. And the Wigner function, we can see the probability distribution being lengthened on the momentum axis and being pinched in the position axis. That's why it's called squeezing. Okay. I see. It's kind of like squeezing that. Okay. Rotation gate. The rotation gate shifts the x quadrature to x cosine whatever minus blah 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 blah. In other words, the gate simply rotates the phase space. Okay. Just rotates that distribution. The displacement gate. Okay. It does this thing here. cubic phase. Okay, so this is pretty. So those animations are definitely helpful. Definitely helpful. Displacement gate. The displacement gate has a specified complex value alpha. It shifts x by a value proportional to the real component of alpha and p by the complex component of alpha. Interesting. I don't see what's the difference. As alpha increases in value, the state is displaced more to the right. Cubic phase gate. The cubic phase gate shifts momentum by this definable parameter, but does not transform x in the position in the phase space below. Okay. Here we can see that the vacuum state has been shifted to a state where it reaches negative quasi-probability. What is the negative? Because this goes up. That's great. That's blah, 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 blah. We use the fog backend and define the argument cutoff dim. The Kerr gate. Before we understand the Kerr gate operates, we should first take another look at the rotation gate in the fog basis. The rotation gate acts with these. In comparison, the Kerr gate transforms. The Kerr gate transforms with these. The square value is what makes the state non-Gaussian, and this transformation transforms the shape of the state significantly. Ooh, fancy. We can see its coherent structure morphing after the Kerr gate is applied at different strengths. For more information about CV gates, see the CV gate section in Surface documentation. Now it's pretty cool, honestly. Really, it's just so that's what that's what those things are doing. So basically, this is a fog engine, Gaussian engine. Okay. See, okay, so I kind of see that. So you've got those two things, and you've got like fancy transformations. You've got momentum and position, and then you've got those fancy transformations in a way that, like, I guess what it means here is the difference is that it's really continuous. Whereas in kind of the traditional quantum computing, you it's not like continuous. Exactly. And what I wanted to do, which I think I'm running out of time for the video, is to go and take a look at some of the example circuits. But that's been a helpful one. So let me check entanglement. Sorry. No, what? Search results. Gate teleportation. Minimizing the amount of correlations. Quantum gate synthesis. State teleportation. Oh, quantum octane. So we can start taking a look at this actually. Why not? 5 minutes, 10 minutes maybe. Why not? Um, hmm. So there is indeed some sort of entanglement um, being used in here. So quantum teleportation, sometimes referred to as state teleportation to avoid confusion with the gate teleportation, is a reliable transfer of an unknown quantum state across spatially separated qubits or qmodes through the use of a classical transmission channel and quantum entanglement. Consider the fundamental quantum information protocol as it has applications ranging from blah blah blah. We know all this. In general, all quantum teleportation circuits work on the same basic principle. Two distant observers, Alice and Bob, share a maximally entangled quantum state. In discrete variables, any one of the four Bell states, or in CB quantum computing, a maximally entangled state for a fixed energy. Okay. And have access to a classical communication channel. Okay. Alice, in possession of an unknown state which she wishes to transport to Bob, makes a joint measurement of the unknown state and her half of the entangled state by projecting onto the Bell basis. By transmitting the results of her measurement to Bob, Bob is then able to transform his half of the entangled state to an accurate replica of the original unknown state by performing a conditional phase flip or displacement for Q modes. CB implementation. While originally designed for discrete variable quantum computation with qubits, the specially separated quantum teleportation algorithm described above can be easily translated to CPQ modes. The result is shown in the following circuit. Okay, so you've got whatever BS, Q012, measurements, but here it seems like so there's some differences. I mean I don't know. I'm guessing, but maybe this is a measurement of the position and a measurement of the momentum. Maybe. Could it be? And then based on these, an X and a Z gate are performed. Yeah, but you're cheating because those are not. Those are not. Are those CB gates or what? This process can be explained as follows. Here, Q modes Q1 and Q2 are initially prepared as the unphysical, infinitely squeezed vacuum state in a momentum and position space, respectively. So this is the vacuum state. Okay, that's really not needed. Before being maximally entangled by a 50-50. Okay, so the beam splitter is what does the entanglement. Seems like. So we're going to check the beam splitter. This is how you do entanglement in CB quantum computing. Okay. These two modes are now spatially separated. Squeezed vacuum state. With Q1 held by Alice and Q2 held by Bob, with the two connected via the classical communication channel C1 and C0 and C1. To teleport her known state to Bob, Alice now performs a projective measurement of her entire system onto the maximally entangled basis states. So she entangles this with Q1 with another beam splitter before performing two homodyne measurements. We'll have to check what that means again. In the X and the P quadratures respectively. Okay. So yeah, as I said, measuring position and momentum. The results of these measurements are then transmitted to Bob, who performs both a position displacement conditional on the X measurement. Okay, so this is a displacement, and this is a momentum displacement. Yeah, so it seems like I'm gonna dive into this more in detail in the next video. I don't wanna okay. I want to compare that calmly. I don't want to make the video too long. It's been definitely helpful. This seems to me like it's basically a similar concept in the sense that you entangle stuff and you just then apply gates based on how you on what you measure, right? And then so in this case it's both a position displacement and and a momentum displacement, because this is also the way you define the Q modes as having um, those two components or variables, this the momentum and the yeah, in so discrete quantum computing you would do a like a flip, or you would so you would do a flip, or you would basically the flip being like you change the amplitude totally from the 0 to the 1 side, or you would do a phase change, so to say. I think so. I think that's really what's happening here. Um, okay, but it starts to make a bit of sense. Let me do another. I'll do another. The next step, I'll really do a Blackbird. So some important notes. Blam blam blam. BS gate. It's definitely a it's definitely a badly chosen name. BS gate. But it's the beam splitter. Okay, so we'll take a look at beam splitting, and then we'll take a look at and we'll make a comparison between these and the other one, and then maybe we'll take a look at other some simulation. Isn't this quantum network? Okay. Okay. Cool. Perfect.